So thank you everybody for joining. This is our first lecture in a lecture series Shyam and I thought would be great to have for our kind of systems and networking audiences. I think our attempt is, or our goals are rather kind of modest. It's an area that we think will be important. We don't quite understand it, so we thought we'd take a quarter and repurpose the system seminar towards kind of educating ourselves. That's where we're coming at from. I think we have a bunch of speaker lined up, and we'll I think schedules are being finalized, so we'll communicate those. But it's my great pleasure to welcome Bruce as our first speaker. And I think as we were kind of drawing up the speaker list, I think Shyam and I were like, okay, Bruce would be kind of perfect. You know, he's lived kind of our world and then taken the time to educate himself on quantum computing, so he can really help us bridge the gap. So it's my pleasure to welcome Bruce, who is dialing in from Melbourne. For those of you who haven't taken undergrad or grad networking, Bruce's textbooks are what we kind of grew up reading these days. And I think he's had a great career across Cisco and a startup that got acquired in the space of network virtualization, and then he's recently retired from VMware as CTO to take on the full-time job as explainer in chief. I think so he's now kind of co-founder of the Systems Approach LLC that you see, and as I understand, I think Bruce has taken on for the rest of his working career this task of explaining complex things to people, and via a series of textbooks and books he's writing. So, with that said, I'll hand it off to him, and I look forward to the talk.
Thanks for the invitation, and it's a great pleasure to be able to give this talk to an audience that will hopefully appreciate it. I'm going to tell you the story of how this talk came to be. But you know, if you know one thing about me, I'm a computer networking person, not a quantum computing person. So take that for what it's worth. But hopefully by the end of this talk, you'll feel a little bit more comfortable around quantum computing. It is an absolutely fascinating topic. I do think there are some topics that are just fundamentally harder to get your head around than others. And I would say everything in the space of quantum mechanics, for me, falls into that category, because basically the way quantum particles behave is really very different to the way we experience the world, because we walk through it, you know, as great big large scale objects, and we don't really have a first-hand experience of how the elementary particles actually behave. But we've got a few ways of getting intuition about how quantum behavior works, and I'll hopefully draw on some of those in this talk. So I want to thank a few people who've helped put this talk together. I worked with a colleague at VMware, David, who probably actually had the job of being the quantum computing expert at VMware. He and I collaborated last year on a talk, and some of his material, he agreed I could use it today. So thanks to David. Scott Aronson is a professor at UT Austin. He used to be at MIT, and I saw him speak there once. And he is the most incredible explainer of quantum computing. He's my hero in this field. He's very funny and a great explainer. I spent a lot of time on his blog.
Yeah, his blog is fantastic. If people don't look at it, it's really off the scale.
Yeah. So I'll make a few references to Scott Aronson today. And I've learned a lot from reading his material. And then I guess I should thank my high school physics teacher, because I can still remember some of the stuff I learned in high school physics, which is very relevant to this. And I think most of you probably took high school or maybe even university level physics. You don't need that much of it to understand quantum computing. You just need to get back in that uncomfortable state of thinking about quantum behavior, which most of us probably don't do on a daily basis. I guess I've got one more hero I want to mention. This is Pat Gelsinger, formerly the CEO of VMware, in my humble opinion, you know, it's an absolutely amazing CEO. These days, CEO of Intel, because he wanted a more difficult job than being CEO of VMware, I guess. So Pat was somebody who I got to interact with a bit, and he knew something about everything. And I remember sitting next to him in a meeting and just being blown away at how deeply he understood everything in the computing business. And I sort of talked to him about this, and he said, Well, you know, Bruce, every once in a while somebody asks me a question and I don't know the answer, but I just make a note and I go and find someone who can explain it to me, and next time I'm good to go. And, you know, I guess Pat never forgets anything, so it works well. So I kind of took that as my role model. And a few years ago, when I was pretty new as the CTO for VMware Asia Pacific, somebody asked me to explain quantum computing. And I pretty much made the classic rookie mistake of somebody who had a very vague idea about how quantum computing worked. I tried to explain it from my understanding, and I got it almost exactly wrong in the way that Scott Aronson will quickly point out that I got it wrong. So rather than just giving you the wrong explanation, I'll just give you Scott Aronson's warning that he gives to everybody at the top of his blog. You know, so Scott, this is the top of his blog, or it was last time I checked. Quantum computers would not solve hard search problems instantaneously by simply trying all the possible solutions at once. Now, why would anybody even think that that was the case? Well, it's actually the most common misconception about quantum computing is you've got these qubits, and you know, we know that quantum behavior means that a particle is kind of in a mixture of different states. So you sort of think it's in both states at once. And so you could sort of think, well, these bits are in multiple states, so I can just explore all the possibilities in parallel because I've got these bits in all these different states. So that's the thing which, you know, the mistake that I made when I first tried to explain it. It's the mistake Scott doesn't want you to make. It's the mistake that lots and lots of people make when they try to explain quantum computing. That isn't the way it works. And so if you get one thing out of this talk, that's it. That's not the way quantum computers work. And what I'm going to try to do in the next sort of half dozen slides is help you get a better intuition for how quantum computers work. From a computer science point of view, if you only know one thing about quantum computing, you might know this, which is that it presents a threat to cryptography. And we'll talk more about this later on, but it is absolutely the case that our existing cryptographic algorithms are under threat from quantum computing. And depending on how bullish you are about practical quantum computers becoming widespread, we're either facing an apocalypse, as the book on the left would suggest, or we've got something we should worry about over the next 25 years, which is probably closer to where I land. And, you know, so there's definitely something to be concerned about here. It's not an immediate cause for panic in my view, but we'll talk more about that as we go. But you should know that as we get through some of the early stuff, we'll just talk about how quantum computers work. Later on, we'll talk about applications. They have a lot of interesting applications, but how they affect cryptography is definitely one that's most relevant for computer scientists. You've probably never seen a quantum computer. I certainly never have, but you can find photos of them lying around. This is a fairly typical quantum computer that's not quite the biggest one out there, but it's on the big end of what's possible today. Every once in a while, you'll hear somebody claim a quantum computer with a lot more qubits than this, but today it's typically in the 50 to 100 qubit range. And we'll talk about what that means in more detail. And the eye-popping thing here for me is actually not all the sort of pretty machinery on the right, which is actually, this is the quantum computer before it goes into the refrigerator. It goes into a refrigerator that lowers the temperature to 0.015 degrees Kelvin, which is to say just about minus 273 degrees Celsius and some equally large negative number in Fahrenheit. Sorry, I can't do that conversion in my head, but it is a very, very, very cold place. So, you know, 0 Kelvin, absolute zero, is the coldest you can possibly get. I didn't realize you could get this close to absolute zero, but that's how cold it is in a typical quantum computer. The reason for doing it at that very low temperature is because at those low temperatures, particles don't move around much. And so there's the opportunity to get something into a stable quantum state where you don't sort of bump it out of its state by having it bump into another molecule. That's my intuition of this, is that you need to get things very, very stable. And the way you do that is you get them very, very cold so that nothing's moving. And at that point, you can get things to stay in a stable quantum state for a relatively long period of time. Not every quantum computer works this way. There's a company in Australia doing some room temperature quantum computers, which is pretty interesting. There's other ways to get there, but you somehow have to create a very stable environment. The ones at room temperature tend to be rather small compared to these ones which are considered state-of-the-art. So let's try to get a little bit deeper into what's actually going on in these devices. But first, here's another warning. This is a fantastic story from Scott Aaronson and Zach Wiener-Smith, who does the Saturday morning breakfast cereal comic strip. So Scott and Zach collaborated on this very, very brilliant explanation of quantum computing. It's explained in terms of a kid sitting in his room reading dirty magazines, except they're not dirty magazines, they're popular science magazines. And his mum comes in to explain that he's not learning things the right way. You should go and read this. You can find it on Scott's blog. But again, it kind of makes the point that a lot of what we understand about quantum computing maybe isn't quite right. I learned some things just from reading that comic strip. Okay, so one thing that you may have heard about quantum computing is this term quantum supremacy. And I first read about it in October 2019 when I was on a business trip, and I was doing what I normally do on a business trip, which is I go out by myself to some place where I can get a beer, and I sit around and I read interesting stuff. And if you sit around in a bar reading things about quantum computing, nobody will ever come up and bother you. So I was there reading about this Google quantum supremacy claim. And of course, the first thing I did was to go over to Scott Aaronson's blog to try to figure out if I should believe this. And so the claim of quantum supremacy basically means that a quantum computer has completed a task more quickly than can be done with a traditional computer. And it's a bit of a fuzzy area, but the idea is that you've done something that really could not be done in practical time by a physical computer. So, sorry, a traditional computer, I should say, and a classical computer. And so what Google claimed initially was that they had solved a problem in their quantum computer, which I think was about 53 qubit size computer. They'd solved this problem, and they said it would have taken 10,000 years to solve this on a classical computer. IBM, who has some very large classical computers and also has a horse in the quantum race, came back pretty quickly and said, oh, no, we could have solved that over the course of a weekend if we had put the world's largest supercomputer to work on it. And the world's largest supercomputer is the size of 2 basketball courts full of equipment. And I think IBM probably had a point. And this is where I say the idea of quantum supremacy is maybe a little bit of a fuzzy area. So maybe Google's claim that they did something that would have taken 10,000 years was not strictly correct, but it was absolutely the case that they solved a problem in a couple of minutes that would otherwise take the world's largest supercomputer doing nothing else an entire weekend. So pretty big jump forward. And I'll talk about what exactly they did. But Scott Aaronson had a very nice take on this. Is this a big overhyped nothing burger? No, it's not an everything burger, but it's certainly at least a something burger. So I think that pretty well sums up my takeaway here, which is that there was something pretty significant here. Maybe not quite the big breakthrough that Google was claiming. And as you'll see, the particular calculation that they did was very carefully chosen to make this possible. But the fact is, they did something that was really, really hard for a classical computer. They did it on a quantum computer, and they did it pretty fast. Okay, so let's try to get a little bit deeper into what's actually going on in these kind of calculations. So, you can't do a talk on quantum computing without talking about Schrodinger's cat. And the thing to understand about Schrodinger's cat, by the way, I don't believe this experiment's ever been done, but the thought experiment is that sitting inside a box, you have a cat, and sitting with the cat, you've got some quantum particle that could possibly decay into one of 2 states. And if it goes one way, it's going to open a a jar of poison that will kill the cat. If it goes the other way, then it won't, and the cat lives. And so depending on the state of this particle, the cat's either alive or dead. And as long as you don't observe what's inside the box, then that quantum particle is in both of those states. And consequently, the cat is also in both states of alive and dead. This is a pretty good example of how it's hard to think about quantum computing in the real world, because you really can't have a cat in both states, alive and dead. You can be ignorant about its state, but I'm pretty sure the cat is either alive or dead. It's just we don't know until we open the box. But the quantum particle really, truly is in both those states. It is literally in the A state and the B state simultaneously. And that's the hard thing to get your head around. And I'm going to give you another example that I think is a bit more easy to understand. But that's the core idea of quantum computing, is that quantum particles are literally in multiple states at once, or as we often say, they're in the superposition of two states. And in the case of qubits, which is the quantum bit, they're in this state of both 1 and 0 at the same time, and they're really in a mixture of those two states. And you will not be able to say it's a 1 or a 0 until you measure the state of the particle or the state of the bit. So we represent a qubit using this thing called a block sphere. And I find this pretty helpful, actually, so you can think of the block sphere as having two poles, a north pole and a south pole. And the quantum state is represented by a point somewhere on this sphere. And it can be anywhere on the sphere. It doesn't have to be just at the north or the south pole. So if the state of the qubit is all the way up at the top, then we say the state is 0. If it's down at the bottom, then the state is 1. But in general, it's going to be somewhere between those two states. And so what that means is that it's a mixture of 0 and 1, and it is literally in that mixture until we measure it. And the thing about quantum computers is they're constructed to keep things in this state for as long as possible, so that you can now do other things to them. So you can apply transformations to a qubit that will, say, flip the position from one side to the other, or to rotate it through 90 degrees, or to move the state from one qubit to another, and to do it in such a way that the two qubits now end up in an entangled state, where the state of one qubit depends on the state of the other. So quantum entanglement's quite central to how quantum computers work. So I'll maybe just spend a second on quantum entanglement. It's probably the other thing that will make your head hurt, along with this idea of being in two states at once. With quantum entanglement, you can have two particles whose states are very tightly coupled, and you don't know what state they're in until you measure them. But if you measure the state of one, you immediately will know the state of the other. So they could both be in this state where they've got a 50-50 chance of coming out 1 or 0, but as soon as you measure the first particle, the second particle's state collapses. And you can take these two particles and put them a long way apart, and that will continue to work. And again, makes your head hurt, but that's the way quantum particles work. So we won't go too far on quantum entanglement because it's a truly tricky problem. But the sorts of things that you do in a quantum computer is you have these qubits, you can put the qubit into a particular state, and it will stay in that state until you measure it. And you can manipulate the states without collapsing them. So you can say, I'm going to move you from, say, one point on the equator to the opposite point on the equator. But when you're on the equator, you've got a 50-50 chance of coming up 1 or 0 when we measure that bit. So we can do the things like that. And that's basically what quantum computers do. Now, what this means is if you want to simulate the behavior of a quantum computer in a classical computer, you need to simulate this sort of behavior. So think of a single quantum bit is described by its position on this sphere, and you can basically capture that with two numbers. You could say latitude and longitude. It's classically done with a pair of complex numbers, which describe exactly where that orange dot is on the sphere. But you can understand the state of a single qubit is covered by two numbers. And so if you want to simulate the behavior of a set of qubits, say you've got n qubits, you're going to have to simulate 2 to the n states. And the simulation, it's not trivial, right? Because I've just described a whole lot of weird things that are going to happen when you measure these qubits. And so imagine that you wanted to write a program to simulate the behavior of a quantum computer. Well, you'd have to go and simulate 2 to the n states. Well, 2 to the 53 is pretty big, and 2 to the 100 is massive. So this is exactly what Google did. When they proved that they had achieved quantum supremacy, they said, okay, the problem we want to solve is simulate a quantum circuit. And of course, they went and did that in their quantum computer. It's really easy, right? Your quantum computer very nicely simulates quantum circuits. That's what it is. Go and do that in a classical computer. It's really hard. And so they found almost the canonical problem that is very, very hard for a classical computer to solve. Not a very useful problem, perhaps, but a very hard problem. And the takeaway here is that you can kind of now start to see why it's so interesting to have quantum computers, why they're so powerful, because a task that is computationally infeasible in a classical computer is computationally quite trivial on a quantum computer. And that turns out to be a bigger class of problems than just simulating quantum circuits. And as we'll see in a moment, one class of problem is factoring big numbers. If you know anything about cryptography, you will probably recognize that's a pretty important class of problem to be able to solve in an efficient way. So hopefully this gives you a bit of an intuition about why quantum computers can do things that classical computers can't. And you notice I never said anything about trying all the answers in parallel. I just said they behave in this very, very different way that's very complicated to explain in classical terms, which means they're hard for classical computers to emulate. There's a pretty big jump from there to let's do something useful. So I'm going to have one more crack at giving you some intuition, and then we'll get on to the applications. So this is my favorite quantum computing experiment, and I'm not alone in this. Actually, Richard Feynman said, this single experiment is at the heart of quantum mechanics, not just quantum computing, but quantum mechanics itself. But I think you can understand a lot about quantum computing from understanding this experiment. This is the one you might have learned about in high school physics. So we start off thinking about classical particles, say ping pong balls. We can fire them at a barrier that has some slits in it, and the balls will go through one slit or another, and they will eventually hit the wall, and they'll line up in these two bands. That's how classical particles behave. Or we can fire quantum particles at a slit. We could use electrons or photons or some other very elementary particle with quantum behavior, and we get a very different pattern. And you can do this experiment. It's been done many times. It's frequently done with lasers, but you can do it with all kinds of different particles, and they will all line up into this set of bands on the detector that is very different than what you would expect if you were seeing classical particle behavior. And the reason that they're doing this is because these particles are behaving like waves, and they're actually behaving like probability functions. And so effectively what happens is the way the particles go through these slits, it's exactly as if you took one set of waves originating at the first slit, representing a probability distribution of a particle going to a certain place, and another probability distribution originating at the other slit, and then you superimpose those two probability distributions. And what the probabilities here are a little bit complicated because they can be positive and negative. And so you can have a positive probability cancelling out a negative probability. And that's why you see the dark gaps between the bright bands when you do this experiment with say, photons, is there are some places where the probabilities add up and that produces a bright band, other places where the probabilities cancel out, that produces the dark band. And you can do this sending one particle at a time. Now, if you send one particle at a time, classical behavior would say it's got to go through one slit, but it will absolutely behave in this way where the probability distributions add up and it works exactly as if it's gone through both slits. So one way to think about this is there's a certain probability of the particle going through one slit, certain probability of it going through the other slit, and as long as we haven't measured it, it's effectively done both things. It's in the state of went through the bottom slit and the state of went through the top slit, and then eventually it hits the wall and the probability function collapses and it landed at one spot and you get to measure it. So a single particle will hit the wall in one spot, but the way that it lines up on the wall is driven by these probability functions. So we're absolutely seeing this superposition of quantum states unfold before our eyes when we run this experiment. And the only way to explain it, it really is that as long as you keep open the possibility that the particle could go through either slit, then it behaves as if it went through both. If you shut one slit, the pattern goes away. If you polarize the particles going through one slit so that some particles have to go one way and some particles have to go the other, the pattern goes away. So only when you leave open the possibility of the particle going through both slits does it actually produce this pattern on the wall, meaning that effectively it went through both slits. Again, this stuff makes your head hurt, but that's the intuition, is as long as you keep the quantum state uncollapsed, keep the possibilities alive, then you will get the quantum behavior that is showing up on the screen. Now, what does this have to do with quantum computing? Well, essentially, everything that happens in quantum computing is about keeping quantum states alive until we measure them, and then superimposing those states in interesting ways to produce interesting patterns. So when you come to do something like try to factor a big number using a quantum computer, what you effectively do is you create an experiment inside the quantum computer where particles are given lots of possibilities to do different things, and then you add them up and you get them to reinforce each other so that you effectively get some bright bands and some dark bands where correct answers add up to reinforce each other and incorrect answers cancel each other out. And so you can think of these bright bands as being almost representative of, like, if I tried to factor a number into its primes, the right numbers would show up in the bright bands and I wouldn't get anything in the dark bands. So that's effectively how quantum superposition and the maintenance of uncollapsed quantum states helps you solve interesting problems.
Hey, Bruce, can I ask a question?
Please do.
So for those of us who don't remember high school physics, so in layman's terms, like, why does observability interfere with the inherent uncertainty here, like, as to what's happening? Like,
yeah, so I mean, this is kind of this is the fundamental question, is that your particle is in this superposition of states until you measure it. This is the Heisenberg uncertainty principle, that when you measure it, you take away the uncertainty and you collapse the quantum state. So you can measure it and you will always find it to be in one state. But until you measure it, it exists in this superposition of multiple possible states. So you really should imagine that the particle, it's fired out of a laser. It has the possibility of going through either slot. And until it hits the wall, you don't know which slot it went through. But if you discover what slot it went through, it's no longer behaving as in a quantum manner anyway. You've collapsed its set of possibilities now, and so it behaves quite differently. So this is like, one way people think about the Heisenberg uncertainty principle is if you measure something, you change it. That's in a nutshell what's going on here, is when you measure a quantum particle, you collapse its quantum state from this set of possibilities to a certain thing. So if I go back to the previous slide, if we have a qubit that looks like this, as long as we don't measure it, it lives in that spot where the orange dot is. If we now go and measure it, in this example, roughly 3 times out of 4, when I measure it, I'm going to get a 0. But then 1 time out of 4, I'm going to get a 1. because it's sort of in that mixture between 0 and 1. And the way I've drawn it here, it's a little bit closer to 0 than it is to 1. So probabilistically, I'm going to get 0 most of the time and 1 a little bit less. If it was right on the equator, I'd be getting a 50-50 chance of 0 and 1. But as soon as I measure it, I'm going to get one outcome. And once I've done that, it's kind of game over. I can't do anything interesting with it anymore. Does that help?
Yes, I think in terms of implications of it, yes. So I guess one thing I was computing in my head is like, should I just treat this as an axiom and try to build my understanding on it, or should I peel this layer itself and try to understand what's behind it? Like,
yeah. So I think this is where you sort of like, maybe with another few years of physics, you could get a bit deeper into it. But that to me is like, the Heisenberg uncertainty principle is a fact, but do I understand why it's a fact? No, it's like, this stuff is weird. I think that's the best understanding.
Got it. Thanks.
Okay, so let's just summarize what we've just gone through. We're about halfway here, and we're going to switch into talking about applications. So what you've got here is that the whole idea of quantum computing is that we have these qubits. We get to put elementary particles into tightly controlled quantum states. We can manipulate them without collapsing their quantum behavior. So we can keep alive a whole set of possibilities. We can combine those in interesting ways. And once we do that, we can start solving interesting problems. So the next part of the talk is about those problems. And I think this is a very quick summary of some of the interesting areas where quantum computing can be applied. And hopefully you took away from this, this is not about trying all the answers in parallel. This is about doing something much more subtle, leveraging the sort of amazing properties of quantum particles. All right, so a really good thing that you can do with quantum computers is you can simulate the quantum behavior of other things. This is not 100 miles away from what Google did with their quantum supremacy experiment. This is basically, if you want to understand the behavior of molecules, well, molecules are made up of atoms, and atoms are made up of elementary particles, and they have quantum behavior. And if you really want to understand how things work at the sort of molecular level, you've got to understand the quantum behavior. So you can either go simulate that in your classical computer, which, as we know, is quite hard, or you can simulate it in your quantum computer, which is perfectly suited for the job. So as you can see, there's lots of work in this area of basically getting a deeper understanding of behavior at the molecular level by simulating molecules using quantum computers. This feels like a very natural one for quantum computing to have a real impact. And even quite small quantum computers could have an impact here. And when I say small, I'm talking about what we have today, which is the sort of tens to maybe 100 qubits. This has been used for things like understanding the evolution of cancer, and this is a reference to a particular paper. I'm not going to claim to understand what's going on here, other than to say that these are people using quantum computing for very practical things to understand the genomics of cancer. Probably a bit closer to the heart of this audience is machine learning. And so you probably know that with machine learning, a lot of what goes on is you're kind of trying to work your way through understanding a pretty big and complicated state space. And so I'm not going to claim to know exactly how quantum computers help here, but this is an area where there are applications of using quantum algorithms to more efficiently to sort of train your neural networks by exploring the state space more efficiently. And so that's another area where there seems to be some interesting applications. And you can certainly, I think you all know that today, machine learning, it's quite computationally expensive. There's a reason we put things like TPUs and similar devices to work in big quantities to train neural networks. So this might be an area where there'd be a gain of efficiency or a ability to learn more quickly.
I had a quick question.
Yeah.
So in some of the papers you referenced earlier, they talk about quantum and quantum-inspired algorithms. What exactly is this? Why exactly is quantum-inspired algorithms interesting? Is it just simulation on classical computers, or what's happening there?
Yeah, I'm not sure I have a good answer for that. I think you will see people, saying, well, I don't have access to a good quantum computer yet, but I've got an algorithm that would work really well if I had a quantum computer. So let's go explore that. So I think that's kind of what I'm seeing. I can't say with that specific paper, I haven't read it, but I do know people are starting to write papers that is talking about how they apply quantum algorithms to a whole range of fields. You don't need to have access to a quantum computer to show that those algorithms will work. Just as we'll see in a minute, the one around factoring prime numbers, it's an algorithm that you can run them on a classical computer, just not as efficiently.
That's kind of basic question, like how do you control what is being computed?
So basically there's a set, this will probably need to go a little bit deeper than I really have time for today, but there's a set of operations that you can do in a quantum computer that are things like, they look like Fourier transforms. I've got an example coming up in a minute of a very simple quantum computation. And so you can do things like, say, rotate a qubit through 90 degrees, where you say, if it's at the North Pole, move it to the equator, and then do that operation again, bring it to the South Pole. Or you can say, take it from the North Pole to the equator and then measure it, at which point you're going to get a 50-50 chance. You can say, take it from the North Pole to the equator and then entangle it with another bit. And now if we measure 2 bits, we're going to see they have the same value, but we don't know what that value is going to be. So there's a bunch of things you can do like that. And some of these things have analogs in the classical world, like Fourier transforms to be a good example. There's a thing called a Hadamard transform, which is kind of like the quantum equivalent of a Fourier transform. And so you can use that for solving problems, and you build algorithms using these kind of operations.
And these are effectively the ISA for what you're programming against?
Exactly, yes. So you'll see this in the example I've got coming up in a moment, that things like do a Hadamard transform, do a controlled knot operation, measure a bit, entangle some bits. Those are all the operations in a quantum computer. All right. Okay, so this is the kind of the last topic I want to touch on, really, which is cryptography. So the famous algorithm here is called Shor's algorithm. It's from 1994. It's kind of amazing. Like, we've only really had meaningful quantum computers for a few years. I think there've been some individual qubits around for a bit longer, but the sort of 50 qubits is pretty recent. But figuring out how to use these things has been going on for 25 plus years. I think it was actually Feynman might have been one of the people who first hypothesized that these computers might be interesting. So the interesting question is, can you have an impact on cryptography using quantum computing? And I should just clarify that there's kind of 2 ways in which people talk about quantum and cryptography in the same sentence. There's a thing to using quantum, sort of quantum teleportation is one of the ways that people are talking about using quantum behavior to send information securely. That's not what I'm going to talk about here. What I'm going to talk about here is how you can use quantum algorithms to attack existing cryptographic algorithms. And so Peter Shor came out with this paper in which he showed that you could solve prime factorization in polynomial time. And hopefully that means something to most people, that we believe that in the classical world, prime factorization is something that can't be solved in polynomial time, and consequently it's at the heart of a lot of cryptographic algorithms. So Shor illustrated in this 1994 paper that if you had a quantum computer, you could solve prime factorization in polynomial time. And that is the heart of why cryptography is now potentially at risk when we start thinking about quantum computers appearing over the next few years. So I mentioned there's this thing called the quantum Fourier transform, which I think is the same as the Hadamard transform, but I'm not quite convinced of that. But anyway, the Hadamard transform is definitely a form of Fourier transform, and the Hadamard transform has a much lower computational cost than a Fourier transform, and consequently you can use it to crack some of these problems. And so the people at NIST have gone and studied this and consulted lots of experts and come up with some recommendations. And so First thing to understand here is that the real threat here is for public key cryptography, particularly symmetric key encryption and hash functions are not really so much at risk because they don't depend on these things like prime factorization. So there are also algorithms that can be used to attack these. So it just is a matter of like increasing the key size. But for something like RSA, which actually does depend on prime factorization, it's simply no longer secure if we get big enough quantum computers. Now, how big a quantum computer do you need for this to matter? One example is, I think the biggest number that's been factored using existing quantum computers is a 2-digit number. Right, so let that sink in for a moment. So factoring a 2-digit number is not a hard problem. It's something that you and I can mostly do in our head. But if the quantum computers get bigger, then they'll be able to factor, you know, multi-thousand-bit numbers, and that's when you have to worry about it. So there is this interesting question now of, you know, we've got today quantum computers with about 100 qubits. How long till we have ones with 1,000, 10,000? That's a little bit hard to predict. But anyway, the recommendation here is that over some period of time, and we don't know quite how long it will be, these algorithms will become insecure. And yeah, so there's the numbers at the bottom there. So it looks like maybe you need 4,000 qubits to threaten RSA. So, you know, that's a bit of a jump from where we are today.
Are the fundamental challenges that need to be addressed mostly in physics and devices rather than in CS to get to this 4,000 bits?
Yeah, that's my understanding. This is what I would call actually an engineering problem. It's quite hard to build big refrigerators at 0.015 degrees Kelvin, and it's quite hard to build things in such a way that you can meaningfully get all the qubits to interact with each other. So it's definitely a sort of device physics and engineering problem to get these bigger machines. But I think the mathematics is effectively done from what I understand. So there's a set of work going on post-quantum cryptography, which is coming up with algorithms that will be resistant to these kind of attacks. So here's a few people working on it. And middle of last year, they announced some candidate algorithms, and I think you probably mostly understand this, but everything we do in public key cryptography is based around the idea that functions are easy to do in one way and hard to do the other. So really easy to multiply together two big numbers, really hard to figure out the prime factors of a big number. So that's an example of a trapdoor function. So I can generate my public key from my private key, but you can't do the reverse unless you can factor that big number, or solve the elliptic curve problem, or any other number of ways that we use to do public key cryptography. And so there's an emerging field of cryptography based on lattices, and I saw a Shafi Goldwasser talk on lattice-based cryptography a few years ago, and all I can tell you is talk about things that are hard to understand. Quantum computing and lattice-based cryptography are both in that kind of hard to understand bucket, but the key idea is that lattices are a sort of mathematical construct that you can create one-way functions that appear to not have an efficient quantum solution, and hence this is being considered as a good candidate for the future of public key cryptography. I will say, studying this has made me sort of regret that I didn't spend more time understanding complexity theory when I was a student. The idea that you should really have a deep intuitive understanding of like the P versus NP problem, and know exactly what you're talking about when you say something is NP hard. I won't claim to have all of those things sorted, but this is the world that you have to live in if you want to kind of go into this field, is you have to really understand computational complexity. And there's a whole sort of set of quantum-based complexity theory of these are the problems that are hard with classical computers, but not hard with quantum computers. So what does this mean in terms of the security of the future internet and everything else that depends on cryptography? So, this is a timeline where I get deliberately quite vague in a few years from now, but, we've already passed through a few milestones. 79 qubits was 2019, quantum supremacy from Google 2020. Well, actually, no, so that was 2019 as well. And, we're certainly seeing confident predictions now of 1,000 qubit computers in the next few years. And so, multi-thousand qubits surely within the next decade would seem a reasonable guess. And the other thing, of course, is with cryptography, you kind of don't want to wait until you know that your stuff is broken. You'd like to make sure that you're taking action sooner rather than later. And so this is why NIST has gotten involved early. And, when I think about this from the perspective of the industry, as a computer scientist, you'd probably think, oh, well, how hard can it be to swap out the crypto algorithm? It's just a module, right? So I think that's kind of a bit of a naive view. And that if you think about, remember the Heartbleed bug from a few years ago and how much carnage that caused, where so many systems had that code running and you had to do this massive audit of every piece of software to figure out, did we have the Heartbleed bug? And so I think this is the kind of situation we have to be thinking about today, is if you're writing cryptography code or using a crypto library today, at the very least, you should be making sure it's really modular and can be swapped out for a different crypto algorithm sometime in the near future. And, if you have the chance, maybe you start thinking about using lattice-based, but think about how we all depend on certificates every time we use the internet. And probably most of you have dealt with certificates at some point. It's really painful to revoke certificates, to, make sure that your certificates are up to date. All that stuff is hard. Just imagine if every certificate became invalid because we just discovered that the cryptography was broken. So you have to be thinking about this sooner rather than later. So just a few parting thoughts, and then hopefully we could have time for a couple more questions. Everybody wanted to see this, I think. This is taken directly from Wikipedia. This is a piece of code that runs on a quantum computer. And I think somebody asked about the instruction set. This is basically the instruction set of an IBM quantum computer. So you can see things like the Hadamard transform, which if you apply it to a bit that's in the zero state, will move it into a state where it's half zero and half one. You can see the C naught. So that if you apply the C naught to a pair of bits, it basically entangles them. And so now these two bits are in the same state, which is to say they're both in the state of being maybe zero, maybe one, don't know, but they're in the same state, so that if you collapse one of them, you're going to find that the other one collapses to the same state. And then, I love the comment, expand entanglement to the third qubit. Just the idea that you can manipulate quantum entanglement using computer instructions, to me, is that's a sign of progress, that it kind of blows my mind. I didn't spend too long on quantum entanglement today, but it's probably the thing that makes my head hurt the most when you try to understand how can it be that I can have two objects separated by a very large distance, and if I measure one, I instantaneously know the state of the other. Faster than the speed of light, I will know the state of that remote object. That's another one that makes the head hurt.
So have people written quantum compilers, or is everybody programming assembly right now?
No, I don't know. I mean, I guess to me, this looks like assembly, right? So I think there is work going on higher level languages, but I don't know that for sure. I do know this company I mentioned in Australia that's doing room temperature quantum computers. They're building a kind of complete quantum development kit. So I kind of suspect that the high level languages are in the works as well.
So my question, I mean, crypto is fine, but as per what you said, like, you switch out the crypto to something else, then it'll be okay. But it also does create a whole class of new polynomial time algorithms, right? Like, what are those? What are the exciting ones? Like, we're not building these things to break crypto.
Yeah, so I mean, I tried to sort of capture that in the earlier slides. I don't know if that was in any sense exhaustive. Well, it definitely wasn't in any sense exhaustive, but I think the things around optimization problems generally, I think, you know, anytime you're looking at something which is sort of an NP hard kind of problem, there's at least the opportunity to consider it to be something that could have a quantum solution. I think one of the challenges here, like just for me to speak about this with any authority, is there's so much sort of active research. Like, we still don't know if P equals NP, right? So like that kind of makes it a little bit hard to say, well, you know, we think that all NP problems are actually the same problem in a sense. But like, I don't think we expect that quantum computing is going to be able to solve all NP hard problems. But that, I think, is, you know, it's all a matter of like the people who work in the space. It seems to me they're chipping away, you know, individually at problems rather than saying we're just going to completely rewrite everything that was previously NP hard.
Well, that sounds very confusing to me. Isn't like the premise of NP hard is that everything in NP hard is NP hard, right? Because you reduce one to the other. I thought there was a whole new class basically.
Yeah, so there are other complexity classes, and I don't have them in my head right now. But there are other complexity classes of the things that are like, you know, quantum hard and not quantum hard. But like, as I say, I'm not, this is where I'm not going to claim to be an expert on complexity theory, other than to say you can certainly go and explore that space and find people working on what are the algorithms that will be amenable to quantum solutions. And
so the assertion is that quantum hard and non-quantum hard are both in NP hard.
I'm not going to even guess at the answer to that.
Okay. Fair enough. That's my level of knowledge at the moment.
So, I mean, anytime I go and read about that space, first of all, I have to go and reboot, you know, the sort of lack of education that I have in that area. But then what I find is that there's all these things that may or may not overlap because of the things that we don't know the answer to. And so, like, you can draw pictures of how all those spaces overlap, and there are some pictures that we know are correct and some that we know are incorrect, but there's a whole universe of possible overlaps that are still, you know, being explored. All right, I thought this is another interesting point, is kind of, you know, how will you get access to a quantum computer in the future? And, you know, this is just kind of my prediction, but I view it as very similar to how we consume things like GPUs and TPUs today, that most people don't have a dedicated GPU farm sort of sitting in their data center. Instead, they have it as a sort of accelerator sitting off to the side of their other systems. And so all of the big cloud computing companies make it easy for you to go and consume some sort of GPUs. Similarly, the big cloud providers are starting to go down a path of you know, making it possible for you to consume quantum computing services as well. The IBM example I mentioned was one of those. So this is just sort of to wrap up, that, you know, obviously what we're going to see is, as these computers become more readily available, people are going to spend more time figuring out good ways to use them, and we'll see more and more use cases. You know, I do think they're really well suited for anything where, you know, there's kind of quantum behavior. That's the obvious use cases, but, you know, clearly things like cryptography show things that have previously been considered sort of too hard might now become not too hard. We have to do something about cryptography. That's, I think, you know, now well accepted. Maybe one point that I didn't really touch on there was that when you store something today encrypted, you probably also need to be thinking about that the way you encrypted it might not be secure forever. And so long-term storage is probably another area where you might think a little bit harder about cryptography, as opposed to, we'll swap out RSA for something else in the future. And hopefully, if I got one thing across clearly today, is that a quantum computer is a very different thing than a classical computer, that there are ways to do interesting stuff with it, but it's just not a simple thing to understand. It's just a completely different computational paradigm, taking advantage of the fact that these quantum particles do really weird stuff. So hopefully that's giving you a bit of intuition, and you won't have to make the same mistakes that I did when next time somebody asks you to explain this at a cocktail party.
Very cool. Thank you, Bruce. This was great. Yeah. I look forward to cocktail parties now. So
I'll have to tell you a story just real quick, which is that somebody at a party did say to me, "So what do you do, Bruce?" And I said, "Oh, I'm a computer scientist." She said, "Oh, that's so boring." And I said, "No, actually, quantum computing is really interesting." And she said, "Do tell." And by the end of that conversation, I had definitely had the best cocktail party conversation I've ever had about computer science.
That's cool. That's great.
It seems to me, just to at least the impression I got from the talk is, it has implications to cryptography. So people are designing lattice cryptography and things which are very potentially could be solutions for them. There's also the people working on complexity theory, understanding what is quantum hard, what is not, and so on and so forth. And there's a third part, which is if you have access to these quantum computers in the cloud, then you can start designing algorithms which leverage that to do things faster. Is that like the three main things?
Yeah, that's a really good summary.
So we should all learn how to basically do basic transforms and basic math, so we can actually be ready for this cloud quantum future.
Yeah, I mean, one of my colleagues told me he'd seen somebody using this for figuring out wireless. Something about interaction between wireless access points, I think. So, so since I know you're a big wireless guy, Sham, maybe you can go research that one.
Sounds interesting. I actually do find the quantum entanglement pretty amazing in terms of communication in general. Yeah.
I mean, and maybe it's worth saying at this point, like, I think you clearly got a sense of like, how deep my knowledge is today, which is like, you've got all of it now, right? So you all know exactly as much as me at this point. But there's a lot of good opportunities to go and learn more. So Scott Aronson has a set of lecture notes. And like when I was reading his lecture notes, one of the things I got to pretty early on was the question of like, why is it that a quantum computer can do things that a classical computer can't? And like, I've tried to answer that question for you today, but it turns out you can't answer that question without really understanding entanglement. If it weren't for entanglement, they wouldn't really be so powerful. And like, do I understand entanglement? Not really. So, but somewhere around lecture 17, I think you'll get an explanation of why they're so powerful. But like, I tell you, there's a lot of hard mathematics before you get to lecture 17.
I think all that makes me want to do is like, just give me a compiler. So let the compiler worry about it, and that's so I can just build cool stuff on top without having to.
This does sort of invite the question. I mean, given your networking background, how do you feel about stuff like the quantum radar and the sort of entanglement at a distance for computer communication idioms? It's not qubits exactly.
Right. I mean, I remember sort of learning a bit about that stuff in the past. It's certainly interesting. At the time, it felt to me it was kind of a little bit niche in the sense of like, people who had very, very sort of strong threat models. I think we're sort of thinking about the idea of like, can we do extremely secure communication using this sort of quantum behavior? I think it's like one thing that is clearly true is that the space of quantum behavior is much bigger than quantum computing, and that other applications of quantum behavior are certainly sort of waiting to be exploited. I guess just a related point is that the the folks that I've spoken to in Australia working on this have talked about a thing called quantum advantage, which is different than quantum supremacy. The idea of quantum advantage is that there are some things that today you might spend a lot of power or a lot of big equipment to solve a problem that you could actually do a better job on, say, a 5-qubit computer. So you wouldn't necessarily do it because you couldn't do it on a classical computer, but you do it because it was cheaper, faster, lower power. And so just like today, we're seeing people pick and choose their different kinds of CPU based on things like power consumption. We might actually see that happen with quantum as well, that it's not just solving really hard problems, but also solving problems that we already solve on classical computers, but doing them more efficiently. So I think that's another interesting space in the sort of the quantum area.
On a related, I think, kind of thinking about related also to complexity classes, like, so is there a notion of computability at all here, like undecidability? Like, are there class of problems that classically we think are undecidable, or are we just like from a computing perspective, like do they kind of expand the envelope of what's computable, what's doable, even in infinite time?
I don't know the answer to that. I mean, I guess like the only observation I can make is like this is not a Turing machine.
Mm-hmm.
Right. But yeah, I think beyond that, I don't have a clear answer to that question.
And we don't have a canonical model of computation yet, like a Turing machine for this world.
I mean, I think the canonical model is roughly it's kind of the quantum circuit where like the things that I've shown you. I haven't shown you the complete computational model, but the idea of things like the qubit is pretty fundamental. There's a whole set of mathematical notation for how you represent them. There's well-known operations like the Hadamard transform and the C-naught, and I think those, to me, that's the sort of standard model of a quantum computer now. Is it at the same sort of level of abstraction as a Turing machine? I'm not sure.
Cool. Let's thank Bruce. Thanks a lot, Bruce, for taking the time out and educating us. This was fun.